go. Hi, everybody. I'm Robert Hryniewicz. I will be your host for tonight. We have fantastic speakers. And welcome to yet another Future of Data meetup. Tonight's session will be recorded, so I want to make sure that you wait with all the questions till the very end. All the speakers will be coming up front and will be taking your questions. And this is the car that we're going to be focusing on tonight. And so after the Q&A session, we're going to take it back and we're going to do another recording and another overview of the vehicle itself. So no worries, there's going to be plenty of time to actually come in and look closely what's going on. And with that, let me begin quickly. Oh, actually, let me quickly introduce what the topics will be for tonight. So Suma, Shivaprasad, and Wangda will be talking about the self-driving car and running it under Apache Hadoop, specifically HTTP 3.0. And there's going to be a demo. Next, Zian Chen will be talking about how to actually train the self-driving car with a simulator. And then finally, Yanbo, Liang, and Wangda will cover the challenges and the solutions in running a Tensorflow on Yarn 3.x. With that, let me briefly introduce this car. So this is a car that I've personally worked on in 2007 as part of the Case Western Reserve University team. This was the DARPA Urban Challenge, one of the first vehicles that we've programmed to drive autonomously. And the key, if you're wondering why does it look like a desert buggy, it's because it was used in a 2005-2006 desert challenge itself. And we got that vehicle and we were tasked to retrofit it for driving in the streetwise conditions. We've had a lot of sensors. I mean, these are, for us, was like, these were the very beginnings. So as you can see, we have a lot of sensors, LiDARs specifically. We have a lot of LiDARs up front, some on the side. Of course, we have stereo cameras, radars, multiple GPS antennas. And the reason I wanted to introduce this with this vehicle is because...
Sorry for the interruption.
Yeah. It's both okay. So the reason for introducing this one is because a lot of things have changed. Over the 11 years, we've changed from programmatically going about setting a lot of if-then statements and specifying how the vehicle should behave in certain situations, as well as what will happen, when the vehicle approaches a city street, city crossing, how would it merge with vehicles, with other vehicles, and all of these rules had to be pre-programmed and preset for this driving behavior. Also, we didn't have a lot of this deep learning techniques back then that we're going to be discussing tonight. Although, of course, as many of you know, all that has been in the making for a while. The actual practical techniques have not been used. So we've used a lot of sensors fusion, Kalman filtering and whatnot to figure out what the camera sees and how to integrate that with laser sensors. We did some basic image processing, edge detections, and so forth. And it took quite a bit of time. And the approach was quite different from what you will hear tonight. Again, this is the vehicle that you see up here on the table. And there's quite a bit of difference, most likely because the actual LiDAR that we use on our vehicle costs about $5,000, which is equivalent to about the price that you can get for just this vehicle with all the sensors. Some of the components that the speakers will discuss here, you also have a LiDAR, but a much smaller one. Actually, this is the most expensive piece in this whole setup. We also had a stereo camera, although for this one, we just have a regular camera set up currently, and you have the power supply for the NVIDIA Jetson, which is the brain of the car itself, and then the power supply. So we'll discuss this farther at the very end. We'll actually take it to the table back there. Shah will discuss it in more detail, and if you have specific questions, we'll be able to answer them and give you more of the technical answers to this. So without further ado, let me just hand this over to the first set of speakers, Suma and Wangda, and this is for you. Oh, Wangda, there you go.
Yeah. So since, yeah, maybe. So today we are going to talk about how to train in self-driving car on the Apache Hadoop 3.1 and also the HTTP 3. So my name is Wangda, and I'm engineer manager at Hryniewicz for the Yarn team. And I'm also Apache Hadoop PMC member and committer, of course. So I'm working on the scheduler and deep learning technologies, and also the GPU support on Yarn. So Suma, do you want to introduce yourself?
Yeah. I'm Suma, and I'm an Apache Hadoop contributor since 2017. And previously, I worked on Apache Actress and I'm a PMC Actress.
Yeah. So thanks, Suma. So today I'm going to talk about the 10 scaled autonomous car. So as Robert mentioned, we will have the NVIDIA Jetson TH2 installed in the car, and also we are using the camera and LiDAR to make the decisions. So this picture is not very clear. So we and our team are sitting in the room and doing some hackathon to figure out how to make the car running. I think this is the first time we get together to working on the car. And this is the first run we did. So you can see the car is driving like a drunk driver. So actually the resolution is not very well. So is it possible to increase this? Yeah. Okay. All right. Let me just. Yeah. So so let me. Yeah. Oops. Yeah. So on this side, this talk about the workflow we are using to make the self-driving car algorithm. So basically, we are capturing the data from the car, which is images taken by the camera, as well as the steering angles. We take the 30K images and transfer this to our HTTP cluster, which runs the Hadoop 3.1 release and also the HTTP 3.0. We use 6 GPUs, and we use this cluster to do the training. And once the training is done, we will deliver this model back to the car. And this is a final run. I think later Suma can show the better videos once she do the demo. So since we are consuming more and more data, and as an average internet user, we will use 1.5 GBs traffic per day. So that's how the Google and Facebook to track you. And also so if we want to do the auto-driving car, it will generate 4 terabytes of data per day. Sorry, could you repeat? So this is just some typical example. So for example, when the self-driving car driving, you have to capture the LiDAR data and also the images taken by the cameras and the engine running data, etc. So there are lots of data to capture. So for the airplane, it will generate more data than the car. Yeah, so since we have more and more data to handle, we need some solution. This is the HTTP 3.0 architecture. So on the bottom layer, we have the storage, on-premise storage, such as HDFS. And this is a cloud storage like S3 and ADLS, etc. And on the right side, we have Yarn and to as a data operation system, which we can manage the jobs and also the resource. So on top of this layer, we can have the real-time database, such as LLAP and Druid running as the container on Yarn. And also we can have the Zeppelin and Spark running inside Docker container on Yarn. So later we can do some demo for this. And also we can run TensorFlow. We include TensorFlow Take Preview in the HTTP 3.0. This can run on the normal Yarn container or running as a Docker container. So we can also do the streaming process, like the Kafka and Storm, etc. And also we can run the Phoenix and HBase on top of Yarn. So on the left side, we have the security and governance, like the nodes and Atlas and Ledger. So with this, and this can protect your data and who can access the data. And on the right side, we have Ambari and CloudBreak, which helps you to manage your cluster. This will be used by the cluster operators. Also, if you want to build your own application, you can have, for example, the web applications and some HTTP services. You can make them inside the Docker container and run and deploy this on Yarn. So this is a training workflow I mentioned. I think later Suma can do a demo, which will be much easier to understand this workflow. Yeah, so let's go to demo.
Yeah. So basically I'll be demoing how you can use HTTP3 efficiently to train a self-driving car and improve, train the model and then improve on it and debug the model, etc.
So do you, okay. Yeah.
So this is HTTP3, which was released a couple of. Oh, it's not. Okay.
So do you want me to?
Can you guys hear me now? Yeah. So this is HTTP3, which was released a couple of weeks back, and it has a lot of exciting new features that were added. And this is deployed with Ambari 2.7. So as you can see, Ambari has been revamped with a new, completely redesigned UI with a lot of usability improvements. So we moved to Hadoop 3 in this version, and Hive and HBase moved to Hive moved to 3.0 and HBase to 2.0, and Spark 2.3 was added. So here in this demo, we'll be focusing mostly on storage and compute. So let's go to the HDFS UI. So HDFS federation was added. Basically, federation was GA'd in HTTP 3.0, so which gives you the capability to scale through by adding namespaces. So here you can see two namespaces that were added, NS1 and NS2. And it's pretty easy to scale by adding a new namespace through the UI. So you just go here and add a new namespace, and it automatically scales. So apart from that, HDFS also added erasure coding, which provides significant savings in storage cost, and also it reduces the overhead from like 200% to 50%. So yeah, let me go to the HDFS file browser view. So the training data for the self-driving car has been uploaded to this folder. It has a bunch of images from the camera, and also we collected the speed of the car at that point and the steering angle. So the images were collected over like 6 to 7 minutes. As you can see, there are like a lot of images which could lead to your HDFS folder being huge, right, in size. So in order to reduce the storage cost, you can turn on erasure encoding with Reed-Solomon encoding. So there are a bunch of options available for erasure encoding. So yeah, let me move on to Yarn. So Yarn, we added containerization support, so you can run containerized apps by enabling Docker. This can run side by side with native apps on a Yarn cluster with very easy configuration. And also GPU scheduling and isolation was added. So this added native support for GPUs, which provides better isolation guarantees between applications. So yeah, basically, let me move to the Yarn UI. So the Yarn UI was completely revamped as well with a lot of usability improvements. So here you can see the cluster level information, and then you can drill down to the GPU usage and availability at the cluster level. Also, if you want to track GPU usage at a node level, you can go to each node. Yeah, so basically here's the GPU information. This displays what's the model of the GPU that's deployed on the node, and the availability and utilization information as well. Yeah, so we also added Yarn, feature called Yarn services, basically that allows you to deploy long-running services or deep learning applications easily in Yarn with very simple configuration. So this is a native edge-based service, a long-running edge-based service which has these three components: the client, the master, and the region server. And you also have a deep learning, a distributed TensorFlow application which has these components. So also we used Yarn service to deploy a Zeppelin notebook, which is again a long-running service in Yarn. So if we go there, so this is the notebook that we use to actually. Yeah, let me make this full screen. To basically train the model and debug whatever is required on the model. So if, yeah, here are a bunch. So basically the first paragraph has a bunch of imports, mainly for TensorFlow, Keras, and Pandas, which are popular deep learning and machine learning libraries available in Python. Yeah, so here is how you can visualize the training data. So here is a sample image that basically was taken from the car's camera. If you look at it, so this is basically the training data, which is the image and the steering angle and the speed at that point of time, right? So if you want to visualize it better, so Zeppelin has a bunch of tools. So here's a line chart which basically allows you to detect how the car is moving. So here it's actually moving straight, and then it took a left turn, and then straight again, and then it again took a left turn. So, and this is the paragraph for training the model. So basically you can run this and on CPUs, which would be pretty slow, but you could hasten this up. I mean, you could hasten the whole process by deploying it on GPUs on top of Yarn. And we'll get because this could take a bit of time. So once the training is done, then you can deploy the model back to the car. So I'll switch to the. So this is one of the first models that was deployed, and this is how the car was running. So if you can see, it's not running that well. So we had to go back and do a bunch of iterations and then debug the model. So you can again use Zeppelin for that. So we use Keras to basically visualize the model and the activation layers. in prediction. So basically, you take a single image and predict what's happening for that image, right? So this is the image and this is the prediction. So somehow the model was cutting the image in half, so it was not predicting correctly, and then there were a bunch of iterations done to improve the model. Yeah, so this is how the final model that was deployed ran. Yeah. Yeah, I think I'll transfer now to Zian, who will cover more deeper into how to train the model using a simulator.
Okay, thank you, Suma. Pretty cool demo. So, and we continue with the presentation. Okay. How to make it full screen? How to make it full screen?
Sorry. What do you want?
Make it full screen.
Okay. So screen and I gotta switch. Swap the space.
Okay. So the full.
What do you want?
So not in the present moment. You can just exit this.
Oh, he wants to go to Zeppelin? Oh, you want to do Zeppelin?
Yeah.
Okay. Which one do you want?
What do you mean?
So you can just full screen.
Oh, full screen.
Yeah. So
On this one?
Oh no, it's a PPT, PowerPoint.
Oh, you want the PowerPoint? Oh, okay, got you. Full screen on this.
Yeah.
And now?
Oh, don't play. Okay.
Oh, just this. Okay, cool.
Oh, okay. So that makes it bigger. Okay. Yeah, we just saw the demo that we can use the physical car that do the training. So let me ask a quick question. So what if you cannot afford this car? Okay. So it's like the 7,000 investment. So what if we don't have this kind of environment or equipment? We can still do the training. So the way we're doing training is like we're using a simulator. Okay. So a little bit about myself. So currently I'm working at the Hryniewicz as a software engineer, and I'm a Apache YAR contributor and works on some of the key features for YAR. So let's us see the overall workflow. Okay. So basically we are using the physical car to collect the data. But if we don't have the physical car, we can also use the second option, which is we can use this kind of simulator here. So like this. We can still collect data using this simulator. And the way we collect the data is that we'll play this simulator just like we did in the video game. So we just like play the video game, play with the car. And we can collect the data with a bunch of images and also another value which is the steering angle. Okay. So after we get this data, we'll send the data to the Tensorflow training program. Okay, we'll train the model, and then we get a trained model. So that basically means that whenever we use a different kind of approach to get the data, after we get the data, the whole process remains the same. So it's just like what we did in Suma's demo. Okay. So let's see how the hardware behind it looks like. Okay. So basically, we have two different the input data. The one is the steering angle I mentioned before, and another one is a bunch of the images. So we have three different cameras: the left one, the center one, and the right one. So we will pump in this data into the NVIDIA Drive PX board, and it's like the contiguously frame by frame pump in. So this kind of, the drive PX board is like the motherboard that set up a bunch of the GPU clusters on it. So we can also, persist this data into the data storage. Okay, so let's see how the software behind it looks like. So see that we already have these two different, data source. The first one is string angle, and the second one is a bunch of images. So we can think this like more like the supervised learning problem. So what I mean here is that we use this image and pump it into the convolutional neural network, and we do the training based on the images. And our focus that we want to get the output of the one single value. So this value is also the steering angle value, okay, the steering angle command. So this will be the output we generate from the training model. And also we have another one which is also a steering angle command, but that one is generated by our human training process, because we drive the car, we get the steering angle at the same time. So we have these two different values, and we want to compare the difference of these two values, and we get the loss, and then we send it back, using the back propagation, and we send it back to the model, and we train the model contiguously. So with the data in, and we will keep doing this process, and we train the model and make the model better. Okay. So we just mentioned that if we don't have this car, we can use simulator. Okay, so how the simulator looks like, how we can actually use the simulator to do the training to collect data. Okay, so I will go through the basic steps, how we can set this up. And this is like, if you can imagine this kind of experiment level things, because this just kind of a simulator, you can go through all the basic process. But if we want to do the industrial level things, this one definitely has some limitations. I'll mention it later. Okay. So the first step is that definitely set up the environment using these binary files. So you don't need to compile from the source code and do all the bunch of things. We already have the binary file ready for you, and you just download it, and you can use the encoder or encoder to set up the environment, the dependencies. So after you set it up, you can load the simulator using Unity. Okay, so let's see a very quick video how the simulator looks like. So. Where's the video? I'm sorry. Where's the video? Yeah. Okay. Okay, as you can see, so this is the interface for the simulator, and we see training model and start the training. Okay, so the first step is we want to specify a location where we want to store the data. Okay, and then we just using the keyboard and to drive this car like you just do in a video game. And as you can see here, we have the angle here. It keeps changing because we are trying to change the directions of this car moving forward. So we will have this angle, three angle data collected, and at the same time we will get different images from the three different directions. So after we finish it, the simulator will replay all the process and capture the data based on our driving. Okay, so we just give a little bit of time for that to finish. Okay, so after it's finished, we'll get the data stored in the directory. So now we can see that how the data looks like. So actually the data, we have two parts. The first part is a bunch of images we mentioned. And another one is we have a CSV file. So the CSV file is like the first three columns are the locations for the images. And there comes for like the four values. The four values are like the steering angle, and the speed, and the throttle, and the brake. So we have these four values together with this, the images. So that will be the full set of our collected data. Okay. So after we have this data, we finish the data collection part, and the second part is that we want to use it to build the training model, and we want to really train it. Okay. So here the basic idea is that we want to build up a 9-layer convolutional network. So the first layer is that we use the image normalization. So the way we want to build this is that you can think about that sometimes the image can be shallow, or there's some lighting over there or something that will print us get the image in a very high resolution or high quality. So we want to avoid this kind of thing to happen, and we want to get a better image quality. Okay, so so the basic idea here is that we try to use this image normalization layer to reshape or format the image that we can get the good prediction in the end. Okay, so after we get this image, we send it into the 5-layer convolutional layer. So after that, we'll send it to the 3-layer fully connected layer. So why we want to do this? The basic idea is that the convolutional layer is focused on the feature extraction. Okay, so we'll get the image from the image normalization layer, and then we will basically use this convolutional layer to create a bunch of filters, and we filter the feature extraction based on the layers. And then but that's not enough, right? Because after we get the feature extraction, we still have something to do, because what we want to do is that we want to gather some kind of output that will become one single value, because we want this kind of single value be a steering angle command. Okay, we don't want to get an image in the end. We want to get a single value. So we use this connected layer to try to squish the image to smaller and smaller, and we use this connected layer to make the image to one single value. Okay, so the code is based on how we demonstrate in the 9-layer convolutional network. And then after we get this data processed, we can directly use this model we built to actually train it. So here we want to mention the limitations that we use the simulator, because if you use the simulator, you can just set up the environment in the local laptop. But if you want to train a model, the model is basically that you have a bunch of images, and you run this program. It can take hours or even days. So that is not doable if you get a very big model to train. So the simulator is just give you the basic idea. But if you want to do the industry level things, we'll still need to get help from the HTTP. Our Hadoop platform. So the key features that key here is if we train the model in the local environment, we take a long time. But if we use the HTTP, basically it takes like several minutes. So it's a huge improvement while using the platform to do the training, because we have a lot of big data applications running on it, and we do it like asynchronous, and we use a GPU cluster to accelerate the training. Okay, so that will be the huge improvement. And after that, we definitely want to, after we get a model, we definitely want to write a test script to test it. So the test steps is pretty straightforward. We just gather the dimensional data, like we mentioned, like the steering angle, the straddle, the speed, and also the images. And we predict this steering angle using our model, and we generate the predicted steering angle command. Okay, so let's show a quick demo how the trained model looks like. So this is the pre-trained model. We just load this model and using the autonomous mode to drive it. Okay, so as you can see, that model here is changed to the autonomous. It means that it's not driven by the human. It's actually the model drive this car to drive forward. Okay, so as you can see that the model is drive the car pretty smooth. We don't hit any other. Yeah. So so that part is actually if I continue, it will back it up. But I just stop here. Okay. Yeah. So believe me, the model works. Okay. I should get 1 second or 2 seconds longer. Okay. So yeah. So that's basically it. So after we get a training model, we can use the simulator again to experiment how the model looks like. Yeah, that's basically the whole process. We use a simulator to simulate the whole training process, like the collecting data, the train the model, and then test the model. So here's the quick reference. If you're interested, you can just download this simulator and play with it. Okay. So now I will hand it over to Yanbo to talk about the challenges we're facing when we do the TensorFlow training.
Hear me? Clear? Okay. So thanks for that very, very impressive introduction of how to reproduce this. So next time, if you play a computer game, your friend will complain. While you always play computer game, you can say, I'm just working. I'm generating the training data for machine learning problem. So after very expressive examples, so I will introduce a little boring technical problem. How to running TensorFlow into production, the challenge and the solutions on Yawn. And my name is Yanbo. I'm currently staff software engineer at Hryniewicz, Apache Spark PMC, and also contribute to other machine learning and deep learning libraries. I usually work on the inception of system and algorithms for machine learning and deep learning. And Wangda, still the same Wangda. Okay. We will explain the scenarios from two perspectives. One is from machine learning's perspective, another is from the infrastructure. Because you can say in our companies, we will build the infrastructure for machine learning and deep learning. And the users for the platform will be far more than the persons who build the infrastructure. If you don't have enough resource or enough quality engineer to build the infrastructure, you can ask Hryniewicz. We can have you to build. Okay. I will first introduction the machine learning problems and the challenges. Just like the self-driving car, we have really, very, very much challenges from the business perspective. Like we can build a recommendation system, we can build natural language processing, and the ImageNet is also very, very famous on the machine learning, deep learning world. So much requirements, most in different kinds of companies. So a good platform can cover all of these problems. It should be very, very suitable for you. So let's say you have two kinds of persons. The first one is like me. I'm the machine learning engineer. So what kinds of problems I'm familiar with? I worked to handle neural network construction, to handle like statistics. We have very strong background about mathematics. And I have the basic programming skills. For example, we only can run some code using Python or using R. We can't handle system environment problem. We can't handle some I/O error, networking error, DNS error. This is really, really a very, very tough problem for machine learning engineer. And if you because the task for machine learning engineer is deliver a good model which can solve your business problems. And their responsible is to build a good model, and the accuracy of the model should be good. And you can, for example, the internet from maybe 7 years ago, the internet, the error rate has been reduced. This is the task of the responsible for machine learning engineer. But they don't want to handle too much system errors. If there are too much system errors, they will make the machine learning engineers work less efficiency. So we should provide a good platform can help us finish the goal. So let's say the libraries or the tools actually used for machine learning engineers, LabLinear, LabFM, and sklearn, very, very famous as the single node machine learning era. And some XGBoost or Spark is also very, very popular. And actually in the HDP, we have cover Spark inside HDP. You can train models use Spark. But the deep learning libraries, usually like TensorFlow or PyTorch or MSNet or other libraries, is also very, very useful for a lot of companies, machine learning engineers, to solve their problems. But there is not a good platform until now. There is not a good platform to solve the TensorFlow deep learning libraries challenges very well. Let's show what features we will want to have for machine learning engineer from what we should do. The first step is we will get the training data and test data. Where is the training data? Usually, training data is maybe large, but the large is compared with other data. For example, you can use Hive or Spark to process a lot of log data. You can build some ETL pipelines. The data is really, really large. You will store the data on HDFS. For the machine learning or deep learning, the input is also very big, but maybe not so big compared with big data problems like Hive and Spark can handle. So HDFS or S3 should be the best place to place the training or test data. We can also share data between different users and different teams because it's a shared storage. And for the Hadoop framework, there can support different computing frameworks like Spark or MapReduce can help us do some pre-processing because the raw data may be included a lot of noisy data or the data you don't need to fit into the model. So we can use the MapReduce or Spark framework to for the pre-processing. And then after we have pre-processed data, we will do some experiment. Do you think we will use all data to do experiment? Right or not? No. Usually the first step is we will sample some data because the first version of your models may be not very good. Actually, if you can get a model, the first version model very, very well, then I think you are really, really genius. Then I think you can ask for millions salaries for each year. So there will be a lot of steps you need to try different parameters, try different neural network architectures, and to say the metrics, to say the loss function change, to say the learning rate change, to say the error rate change. So there will be train many models. The first step is we will sample some data from the full data set, and then we will choose some state-of-the-art model and tuning the hyperparameters with cross-validation. So in these steps, the most common case is single node with CPUs or single node with GPUs. This is the case for the consolidation of some small models. After that, we have trained thousands of models, and we found this is the best one. We will try to put the models into the whole data set. Because at last, you will use the model for the whole data set. So this is the best model. And at these steps, we still need to train the model, but we don't need to change too much for the neural network architecture for the parameters. We just to make the architectures running on the whole data set. In these steps, the multi-node CPU and GPU cluster is required. So you can say the last step is to put the model into production. So you can say almost all the steps will involve different types of training. Single node, single CPU, and single node GPU or multi-node. A good place, a good platform is we can use one framework to do everything. Let's show an example, very simple examples to say how it should be. There are some overlap video compared with Suma's demo. So I will quick pass the overlap and show the difference. The first thing is we want to get the training data. We use the HDFI browser, and we store the data here. The data is, you can say, if you have some experience or working with TensorFlow, you can say TF record is the standard data format for TensorFlow. You can get a lot of free data set from internet. And there are three data sets. Is the the data set is not so big because we just want to demo it can work. Actually, the DFS can support the very, very big data set. After that, we will get a model. You can write your own model, or you can download some models from the internet. We just use the models download from Google's TensorFlow models repo. The model is CFA10, very, very famous model. It do image classification, whether the image is a cat or dog. So we didn't change any code for the model. You just download it and use it, or you can write your own models. The next step is very important step. We will show the very simple command to help you submit the job, submit the model training to Yawn. You can say we have a run TensorFlow command, and there are two parameters, two arguments or parameters. The first one is a configuration file that you will specify some parameters for the job, and another one is a Docker image. Because you want to train the model with GPU support, there should be have some Docker can support the GPU. You can see the configuration file. The first is the name, and you can say there are different roles in TensorFlow job. If you are a single node job, there are only one rows. But if you train a distributed TensorFlow job, there will be different roles. For example, the master, the parameter solver, we call it the PS, or the worker. And for each row, there will be a submit command line. We can say, we specify there are one masters, and the master has 4 CPUs and memory and GPUs. And this is the launch command for the master. And you can say we specify a job directory. The job directory is very important. You will save the models and the checkpoint to the job directory. And for workers, we did the same. So this is a configuration file for users should config. And actually, the file will be keep changing because Spark TensorFlow on Yawn support is under actively developed. And at last, we will support it for the TensorFlow TensorBoard server, because we need to start the TensorBoard, and then we will start the jobs using this command line. You can say we finished submitted job just finished, it started to run on the Yawn cluster. Then we move to the Yawn cluster. You can say this should be quick path, just like the Suma mentioned. We can say we have a GPU resource in the Yawn cluster, and other resources like CPU or memories. And after that, we say the service. We found out we just submitted service is distributed TensorFlow. And then we click the server's name. We can see the detail of the service. There are one masters, one PS, one TensorBoard, and one workers. And each configuration for vehicles and for memories for GPUs. This is the overview of the job. And we can also see each job's log from this page. Because for a machine learning engineer, they usually want to see the learning rate change or the loss change. We need to provide some ability for them to show the logs. Maybe they will print out some logs for the results the results requested or used for their program. And then we can start the TensorBoard. Very, very good features for TensorFlow, because each machine learning engineer want to learn the progress of your jobs and the graph, because TensorFlow will compute a neural network. The neural network actually is a graph. You can check everything from TensorBoard. This is the graph. Because Shivaprasad is very, very famous. This graph, we usually don't need to change too much. And each of the projector will show the features, because some of the features you need to, you want to say the status of the features or the features change. So there will be a web page for this. And the most important is some summary information. The TensorBoard shows it like you run other TensorFlow jobs in other platform. The accuracy, the global step change, and the loss change is very, very important for a model. So for machine learning engineering, we can get this from the page. And after that, you can say the job has started to train, and the loss continue decreased, and the global step for per second is keep going. And after that, we can say where we save the model. This is the directory for saving the model. The model saved in the directory just like any other TensorFlow jobs. You run on Google Cloud or run on Kubernetes or on others. You can use this directory to export your model for model serving and for model prediction. So this is the whole steps of training the model. After the job have finished, you can say we have kept the last step of the model, and you can use the model for further processing for model serving. So this is very cool work that has been done for the Yawn team at Hryniewicz. We didn't, from the machine learning engineer, we didn't handle any details because we don't want to do it. But there are a lot of issues need to solve to make it can work like this. And Wangda will talk about the details and what they worked to make this happen.
So thanks, Yanbo. So I will take over to talk about how from your side how we do the infrastructure to make this can happen. So for the machine learning, you can see from the infrastructure is like this. It is just the tip of the iceberg. They want everything to be super simplified. But the reality is we see a whole bunch of things we have to handle. So there are some important things we need to do to make the machine learning engineer life easier. So first is the packaging and dependencies. So you can imagine that as a machine learning program, they may require different version of Python and different version of TensorFlow, and they may want some other Python libraries. Install everything on the on your own laptop is not so easy. And if you want to install everything on the server and the server is shared by everyone, this will be a nightmare. And for the second thing is for the GPU isolation, because as you know, the GPU is very very expensive. Everybody wants to use more GPUs, but we have limited resource. And also, if we make the several applications to land on the same GPU, it may make everybody's cannot work, because it will cause some funny out of memory issues for the GPUs, etc. And they want to share the same file system to get the data access. And they, the machine learning engineer also wants to track in their running jobs to see what's going on to their job. And the last is they want easy to deploy their jobs. So when the machine learning engineers do the experiment Yarn, so this is what the Yanbo covered before. So first, they want to sample the data from the large data set. So there are many Yarn applications are designed for this, so such as Hive and Spark. So for the two, they can do much more than the sampling, but they are really good at doing this work. And what if you don't have the GPUs on your laptop to do the experiment? You not always asking your boss to buy a latest alien GPU game laptop to do your training works. So what you need to do is to pack your dependencies to a Docker image and launch on the by using the Yarn services. So when you do the machine learning experiment on Yarn, so as I mentioned, we will first pack your dependencies, so which could be a Docker image. And also you can specify a resource and GPU resource in the Yarn service spec. So here is the example. So we can specify what's the Docker image, and here specify what's the launch command. Because we are using, and so this example is showing how to do the Zeppelin to do the training. So you just to call the Zeppelin command to launch the Zeppelin notebook. And also you can specify the CPU memory and GPUs. So on the right side, this is a page on the Yarn UI which we can use to deploy the service. And actually, we are very actively to trying to simplify all this process. This is some an existing solution, and after some time, we will make this to be even easier to be used. So once you got the experiment done, you can deploy your training code to the production, and you can run it daily, run it weekly, like that. So just to run the submit tfjob.py and specify the input spec and specify the Docker image. So I'm going to show the example of the spec file. So this is spec file. So you need to specify. So this spec file is a standalone TensorFlow job. It only runs one worker. You specify the component as a worker, and also you specify the resource and what's the launch command you want to use, a number of containers for this component. So if you want to distribute it, TensorFlow, you just need to add parameter server and master component. And Yarn will do the wire up for everything, and it will also automatically generate the tf_config environment. So all these components can understand how to talk to each other. So if you want to have some end-to-end tutorials, you can check the GitHub to get the code. So here we have end-to-end example about including the script and the Docker file. So you can use that to do that on any 3.1 cluster. And I'm going to talk about some recent works to support machine learning workload in that TensorFlow. So first is I'm going to talk about the GPU isolation and scheduling. And for the native service, I think for this meetup, I'm going to skip because of the limited time. And all these things are available in Hadoop 3.1. So for the GPU support, first question is why need isolation? As I just mentioned, if we have multiple processes to access the same GPU, the access will be serialized. So only one can use GPU at one time, and the GPU will swap and that out and let the other one in to do the task. So NVIDIA provided MPS to allow the multiple process to use the GPU and to share the GPU, but that one is not commonly supported by all the deep learning platforms. And also this will cause out of memory easily if they are not using the MPS. So for the GPU isolation on Yarn, what we're going to provide the granularity is everyone can use from 0 to n GPU device exclusively. And also, we are using C groups and Docker to enforce the isolation. So when we use C groups, we will use the devices subsystem, and we will give the devices not allowed to only access to some PCIe device, which is pointing to the GPU 0 or GPU 3, for example. And also, when we use Docker, we will just pass the -- device and specify the GPU devices. So the Docker internally will also use the C groups to do the isolation. And for the GPU plus Docker support, because many machine learning platforms relies on this, like Python, R, or different version of Udian, CUDA dependencies, we need Docker to solve these dependencies. However, when the GPU is come into the picture, it was not that easy because so there's overlap of this. So I think it's better to play this slide. So for example, when we have the host OS, we have a GPU-based library which is includes the driver. When the driver version is not match the driver version inside the Docker container, the launch will fail. You cannot get any result. So instead, we using the NVIDIA Docker plugin which will help to automatically mount the NVIDIA driver, etc. when the container gets launched. So like the picture in the right, in the Docker image, you don't have to worry about the GPU driver. So the NVIDIA Docker plugin will just mount this one to the Docker container when the container being launched. So this can solve a lot of dependency issues. So for Yarn, we support GPU on Docker isolation by using the NVIDIA Docker plugin. And finally, by using Yarn, we can make the cluster can be shared by different applications. So let's say we have a cluster which don't have GPU. We have 5 nodes, which deploys Yarn. And we can run the batch applications like tests, and we can run the Spark as well. And some applications we can Dockerize. We can run some Spark applications inside Docker container. And we can run the LLAP application for the interactive queries. And once you have some budget to buy the GPU node, also deploy the Yarn on this node. And on this node, you can run TensorFlow inside Docker or outside Docker. And you can run some other applications like Caffe or MXNet. Yep, I think that's all.
So this was really cool. So let's go to, before we jump into the question section, let me make sure I turn this microphone on. All right, so brief recap. We've seen quite a bit of it today. I've started with the discussion of the car that was a little bit over a decade ago, where you had these, hand rules that you basically had to, pre-configure to get started. Then we went through a car that you essentially drive, and you train it to figure out what images correspond to what type of behavior. We went through the architecture, what you can do with Apache Hadoop 3.1 and specifically with the HTTP 3.0 product line. And then, of course, the solutions and challenges and best practices of actually deploying TensorFlow, of going about it, and what you can do, and what hardware is required. So with that, what we're going to do is we're going to open up to the questions with the entire team. I'm going to have the microphone to walk around. After the Q&A, we're going to split into groups. If you just want to walk up and ask them questions offline, they'll be there. We're going to, again, take this car to the back of the room, where Harsh and I are going to have yet another talk about some of the details, some of the hardware details of the car, if you're interested. And after that, we'll wrap it. We're going to close it by about 9 o'clock, the latest. Sounds good? All right. So with that, let's open up to questions that you might have. Also, if you're online, if you want to post any questions in the meetup group, I'll be also checking them as well. So you can get to that. And finally, this video is also, as I mentioned, recorded. So there's a link in the meetup group if you want to rewatch it afterwards. And we'll also be posting the slides as well. So all of that is going to be there available for you. With that, let's start with questions. So any questions that you guys might have right now, I'll pass around the microphone. All right, I'm going to go back. And, no, so just
Okay, I repeat the question. Okay, I repeat the question again. Talk about the sampling technology used for the training data set sampling. Because different users maybe have different preference. Usually, currently, maybe for big data, the most popular use is like Spark or Hive. And you can sample some data according like a random sampling or according some key columns. For example, you will train the first 3 months. You will take the first 3 months data as training set, and the following months as test data set. Because some of your model will have some more time-related features. So this and actually the logic is defined by some like UDF or user or your own ETL pipelines. But the framework should be like Spark or Hive. Yeah. Other questions?
Any other questions? All right, all the way in the back.
Hi, I have a question about Yarn. If I have a hybrid environment, assume that all the machine has GPU.
Yeah. So yeah, sure. So the question is, when the cluster has mixed GPU and CPUs, how we can make the applications which need GPU to run on the GPU node? I think that's the question, right? So basically, I think this is a good example. So on the right side, because in Yarn we support a feature called load label. So when we want to schedule applications on the GPU node, we can just specify to allocate the applications to the GPU node. Another approach, if you don't like the node label, it's also fine, because each application which want GPU, they will ask number of GPUs. And the Yarn scheduler will look at all this load in the cluster and to see which node has enough GPU to run this job. So let's say if you on one single container ask 4 GPUs, it will look at all these nodes which has 4 unallocated GPUs, and it will launch the container on that node, and it will make the job can get their own asked number of GPUs. So does this answer your question?
So that means those nodes that has no GPU will never get the GPU job. Is that correct?
Yes, correct. Because from Yarn's scheduler perspective, when you ask more than 0 GPUs, and it will never allocate the resource to the 0 GPU node.
Thank you. So actually I have one quick question.
GPU. Oh yeah. So we recently we published a GPU blog today. So this is part of this question. Yeah, hotmonster.com. And this one. Yeah, so we published this blog post today, so which has a very detailed information about how we configure the GPU node and how these things works.
Cool. So I'll post that link in the meetup as well. So quick question for you guys. So you've trained us in what, about 90 days? The whole, so it's driving like a teenager essentially. What were like some of the biggest challenges in actually designing and then having the car to actually drive in that arena at the very end? Like, what were some of the biggest gotchas, like something that you wish you've known before you started training the car?
Yeah, so this is a good question. So first thing is first thing we learned from this car is it is running in a different OS. It called so basically the base OS is Ubuntu. But on top of that, it's running the ROS, so it has some different concepts. So every row sending message to each other and to make how how we can capture the data and how we calculate and how we send back to the car. So that's the first challenge. And when we trying to design the model, initially we are thinking this could be some easy problem because it's only trying to follow the middle name, right? So we have a very deep dense model which is similar to the linear model, and we use that to deploy it to the car. We trained that for about 10 minutes, and we deploy that to the car, and car is driving is very randomly driving forward and backward. so then we had to go back to read some plots and to see some existing solutions to see how this works. We spent maybe 1 week or two to finally get some workable model, and for this one, it even takes longer.
Is your car always going to drive like a drunk driver?
So do you think this is this one driving like a human? maybe it's more agile than a human. That's why.
It's more like a truck driver.
So can I ask the question? So when you're driving, after drinking some wine, can you drive like this? Yeah. So any other questions?
Is the testing that's whole, so you have trained this for this specific track, right?
Mm-hmm.
And once you train for this specific track, and if I try to run the same car in a different track, which has a trajectory like up and down, whether this model will work, or do I need to go for the training? That's a one part. And in general, in the industry, right, and in reality, is this the supervised learning using deep learning is one, or we also need to use reinforcement learning to do a real world application of the self-learning?
Yeah. So this is a good question. So the question is, when we trying to train the car model in this track, can we generalize the model to make the car can run on the different track? So the answer is mixed. So basically, all the machine learning can do is it will try to learn from the training data, and so basically its knowledge will not go beyond that. So what you teach the car is it will not think about something new and give back to you. However, by using some technologies, for example, the deep learning, it will make the model to be more generalized. It will, so for example, when you trying to deploy, when you're trying to design a model to utilize the number in writings, some very naive models may only say the exactly writing like you, it will recognize. But if some good models, they can learn from millions of people's writing and get some better understanding of how the writing should be. And also in the model, we can pre-process the data. We add in some noises to the data. We can make the image to be more shadowed or more overexposed like that. So we can make the model to be more generalized. Yeah, but for this car, for this model itself, because we don't have, we haven't do much words to make the words to be generalized, and I haven't tried, but I expect this doesn't work.
Thank you for the session. It was really helpful. I had one question on understanding the accuracy of the model. You mentioned that along with the labels assigned by the CNN model, there was human understanding involved to check how the accuracy of the model is. So how did you go about doing that, given the scale of the data?
So sorry, I'm not fluent.
How did you test the accuracy of the model?
Yeah, so the question is how we can test the accuracy of the data. So basically in this model, what we used is the image and the steering angle. So the car is driving in a constant speed. So you can see that the input will be the image, and the output will be the steering angle. So for this case, we just try to say when we trying to control it by a human, we will get the steering angle, and once the model is generated, we will have some separate data set which is not as part of the training. The training program never see. We will use that to predict. We will give each pictures to the model to say what's the steering angle should be, and the program will compare the output steering angle with the real human steering angle, and so that is we can use that to calculate the loss function. Yeah, so there are many papers. So because the self-driving car, so the question is, how can we know how to do this algorithm? So because there are many papers talking about self-driving cars, so this idea comes from one of the NVIDIA's paper about the self-driving car. I think previously Zian mentioned the car simulator. If you go to that link, there will be a link to the paper. You can find the paper on the GitHub link.
Earlier in the presentation, you showed some simulations. Can you use deep learning for the simulation to train the model too?
So just trying to understand the question. So I say that for this car, do we use a simulator?
Yes, the model. Did you use the simulation to train the model as well?
Yeah, so let me repeat the question. So basically the question is, when we're trying to train the model for the real toy car, do we use a simulator to train the model? So the answer is no, we don't use a simulator, but for the ROS, it provided a simulator. So actually you can use that to do the simulator to do the training, but we didn't use that.
Time for 2 more questions. One more.
So with the scale of data that you had, did you run into any performance issues? And how did you, do you have anything in the platform that can, make the performance or the data pre-processing faster?
Yeah, so the question is, do we run into any performance issue? So when you're using your own laptop, you will run into many performance issues. But by using the by using the Yarn on HDP, so basically, this model training was very fast. It takes several minutes to finish. So if we are using 30K images to train, so that's comparing to the real world case is still not still a very small problem. Because we only take the data for about 10 minutes to get the 30K images. But if you running the model for 2 months, running the car for 2 months, you will have lots of data. So in the real world, for sure, you will have lots of performance issues too. Some possible solution is like you can downscale the image when you do the training, for example. And also you can train the model by batch. So you can train the models in the sunny days as a model and in the rainy days as a model, like that.
So let me wrap up with one final question. So what is the plan for the future? Where do you guys plan on taking this? This car, farther training. What do you guys have in mind?
Yeah, so the question, so do I need to repeat? Okay. So yeah, our plan is to sell this car. Yeah, so this is a joke. So I think by using this platform, we can learn a lot by how we can train this model in an even larger scale, and we can try to solve the problems like can we make the models to be more generic. And also we can demonstrate how by using this to showing the values of how HDP is given to the users, how the Hadoop and Yarn given to the users for the end-to-end life cycle.
Excellent, guys. This has been really, really wonderful. And one more time, big applause for these. What we're going to do is for the offline, just come over here and talk, and we're going to take this car and we're going to mic up Shah over there, and we're going to have another discussion in the back, just focusing on the car itself. So then we can split in 2 groups and not be too crowded. Okay? Thanks.
No, I think it's good. There's a lot of light.
Probably a little bit brighter.
Oh, okay.
So the light is
Oh, so, yeah. Yeah. Can you hear me? Can you hear me? You can hear me. Can you hear me? Yeah. Okay. Yeah.
Is it good too? No? 1, 2, 1, 2. Can you hear me?
Yeah.
1, 2. Wait, let me just look it up here. How about now? Now, 1, 2. George, can you hear me? George? Yeah? 1. Okay, I'll try to be loud. Okay, done. All right, we got the camera ready?
Yeah.
All right.
You want to come here?
Well, it's going to be you. So Harsh, could you go around and explain in more detail about different parts of the car and what they're responsible for, and then how it fits into the
Sure.
architecture?
Sure. So I'm going to start off by the most expensive piece on the car, the lighter over here. It alone. No, the car costs $6,000. The lighter itself is like about $3,000, and that's why we said 1/10 autonomous car. A Tesla is 60,000. This car is $6,000, so it's 1/10 the cost of a Tesla. That's lighter. We had a stereo camera before. Then some complications didn't occur, and high resolution. We wanted a lower resolution camera for faster processing as well. We didn't really feel that we needed really high resolution images for the same level of accuracy required. So we just put in a simple camera up here. This is the battery for the NVIDIA Jetson TX2 card over here. Then the battery for the car usually goes down here, which powers the car, and you connect all the peripherals around here. So what this is running is it's an Ubuntu OS on the card itself, and I think as engineers mentioned, there's also another OS, the ROS. So that's what we're using to deploy the model, the ROS launcher. So some of the commands on that end, and every time. What we did while training was we actually manually drove the car around the track, made sure that it followed the red lines, what steering angles were associated with that, what was speed, and then we had an SD card. We hooked it up with our computer and transmitted all that data back to our cluster. Had the model trained and deployed the model back onto this car. So we wanted to set up more of a wireless interface, but we weren't able to get to that position. But that's a high-level, architecture. What you would say the construction of how the car was, made. So if you have any questions regarding that,
OS that you mentioned,
yeah,
have worked on ROS.
Yeah.
So both are sitting side by side, or the ROS on top of the Ubuntu?
R is on top of Ubuntu. Yeah. So we're running that on our on the terminal on our Ubuntu. Yes, correct. Yeah.
So Ubuntu is
Yeah.
not right?
Okay. Wait a minute. Okay. So the question was, is the ROS running on top of Ubuntu? And so the models are deployed via ROS, which is running, which is on Ubuntu. Yeah.
So Ubuntu you log into this one?
What?
This is the.
This is the battery. This is the battery for the NVIDIA Jetson 2.
So where Ubuntu? Where?
On this card, the Jetson TX2 card.
This card they have Ubuntu loaded.
Yeah, it has Ubuntu loaded on that. Yeah.
So one of the reasons you might be wondering why are we using a powerful graphics card, and the reason is that this is a parallelized model. So when we do make the predictions, when we do what's called the inference, we need just as powerful the parallel processing system. So that's why it's using that specific hardware for making the predictions in real time while the car drives. Yeah.
So once the model's deployed, it's processing the images and. No. So what happens is once the model is deployed, it's predicting a steering angle for the image that it sees, the frame that it sees at that moment of time. So that's why you see the car behaves still. It's not there are comments it doesn't drive like an adult, it still drives like a drunk human, but that's one of the reasons why it's not. It's trying to predict a steering angle based on the image that it sees at that moment of time. Yeah.
We are amending
Yeah.
the running model. We're amending the model when it's running.
So,
Our job
yeah.
is run model.
Yeah, we're running the model that's that we trained on our Hadoop, yeah, HTTP cluster, yeah.
HPC is not by itself generated.
So the model has been trained
And then offline, and then deployed onto this car.
My question is, why
Yeah.
you want to deploy GPU here? Why you use so high-end embedded system? Why?
Probably the processing capabilities. First thing, you want to process in real time. Yeah. So yeah. It's not something that's That's why. Yeah.
So the problem is, can you explain me again why the car is not driving best right?
Yeah. So it's two. So the question is, why is the car still behaving a little bit erratically? It's a couple of issues. First of all, this was a much larger car compared to the track we had, so it's a longer wheelbase. So the turning radius was not as sharp. So we had to make sure. That's why we had to use a lidar. If it was running into objects, it could go back and realign with the red line, and then go from there. That's why we had to use a lidar, and because yeah, that's a lidar. So when it's hitting an object, it needs to go back and reposition itself so it has the red dotted line that it's following in its point of view.
But it's not the part of the training.
Yeah, that was not a part of the training. That was an added part.
You
Yeah. So
something.
sometimes
more
because
of a safety feature.
Safety feature, yeah. Because if you look at a Tesla, it's not just the cameras that are driving the car on an autonomous mode. It also has other redundancies, like all the other sensors, to make sure that it stays safe. So that's one of the things we had to incorporate when we were, initially this was not the part of the plan, but we had to incorporate it just because the challenges of training it within a confined track and not having the car turn as sharply as we would like it to. Those were the mechanical challenges that we faced.
How about the line? You did not follow the line.
Yeah, it would follow the line. That's what it was trained on. Yeah. So if you see from the demos, it tries. So it's
Not very
yeah.
sometimes.
Yeah, so the model's not perfect. So it's something that we're still developing. Yeah.
So this is the expensive definition.
Yeah.
And if you see that autonomous vehicle on the road, you see some kind of things which is rotating in front of the car. So that is also the lighter.
So the question is, in autonomous vehicles, there's a rotating sensor. Is that also called a lidar? I'm not sure.
So what they do, for example, on the Google cars, it's a rotating. It's got a 360 view of the entire space, and you can actually watch some YouTube videos where they've recorded how that laser sees the environment. And so it's not like a visual event, like a camera, but it sees these dotted points and these really straight laser type mapped into, I don't know if it's like a 30-degree angle of the entire environment. That's how they do it. So it doesn't turn around. It does have like a one plane, very fast.
How much does it cost? I've always understood the lidars were expensive.
So what's the cost of this one?
The lidar?
Yeah.
It's close to $3,000.
$3,000.
Yeah.
Smaller
Yeah.
than the things you see on top of the car.
Correct. Yeah.
So the one that I've showed at the very beginning, those were, back then it was about $5,000 to $6,000. So
on the DARPA car.
On the DARPA challenge,
DARPA car.
on the very first car. So they're really heavy, and they require a lot of power. So now for that one sensor, that one laser, you can buy entire car, vehicle, and simulate it on your own, which is the really nice difference that we're seeing.
How much is the cost for the NVIDIA board?
I'm not sure about the cost for the NVIDIA board itself. More than about, I think, close to $2,000 as far as I know. But after the lidar, the cost of the car was $6,000. Yeah, I have to ask my manager what he paid up for this. Yeah.
We all 20 is base. Driving mechanic.
So
chases that you can buy. So this chase, so normally this would be a remote-controlled car, but it's retrofitted, so some of the parts were taken out and basically hardened to. There are springs that can take more weight because of the weight itself of the vehicle.
and the chipset, everything was soldered on to the car. So we had engineers soldering this onto the car, and all the circuitry that was required to the sensors. All this is all soldered on to make sure it works with it. Yeah.
You say you have
Yeah.
three kind of
Yeah.
camera, right? This is one, right?
That's one. Yeah, we had a stereo camera. Then there's a lidar. That's a sensor. So that's in terms of sensing. Those are the only two things that we have for this car.
But,
Yeah.
but
Yeah.
I think the image you take from this car, right?
Yeah.
It's different than the image from the training model, right?
No, it's the same.
But
So the one on the picture, that was
Yeah.
the stereo camera. So there's another way you can train these cars. When you have, so basically when it's a stereo camera, there's two cameras, there's a certain distance between the two lenses, and that allows you to do, so for example, your eyes, when you look around,
So it gives you a depth
the
of vision.
stereo vision gives you a
Yeah.
perception of depth.
Yeah.
So that's another thing we could do. For this model, we realized we don't really need that much processing. We only needed this camera to focus and detect the angle from the red lines, like you've seen on the video,
Yeah.
and then this one for the safety, if
Yeah.
it for some reason the hardware components allowed it steers too aggressively
S-
and it gets out of line, so this way it could back
Yeah.
up and again follow the red line.
And so for the stereo cameras, that is something that we can look to incorporate in the next iteration as we improve this. So that gives you a depth of perception. And so yeah, so
So
yeah.
the
Yeah.
data you
Yeah.
collect is for training is real data.
From this. So the data that we collect for training, it's collected manually. So what we do is we actually turn the car on and we manually drive it around and make sure we follow the red line. And then we collect the steering angle and the speed, and then we train it on that, and then we deploy it back to the car.
So
Yeah.
when you're driving, you also by yourself. You also
No. Once it's deployed, it's autonomous. We don't touch it anymore.
The question is, first we
Yeah.
drive it around the track, sort of
Yeah.
like you've seen in a
Yeah.
simulation engine. You drive it in the simulation engine, you collect that, and then the idea is the car learns on its own how to drive it, right? So if you're not the best driver, the car, also won't be just as good, right? So if you were a drunk driver, again, coming back to this.
So
point.
that's exactly one of the challenges we face. So when we were training it around the track, the car was not agile enough to turn sharply enough for all the turns. That's why it behaves.
so the car
Yeah.
and the
Yeah.
data you collect,
Yeah.
the car
It's
not good
the
enough.
data is not perfect because of that reason. Yeah.
Have you ever run this in a low light condition?
We ran it on a condition where there was a lot of glare on the road, but not a low light condition. Yeah.
Do
Yeah.
you think it should handle it, or would you have to do a whole different set of algorithms? Different hardware?
That is something. Yeah.
So we've
yeah,
actually
yeah.
tested it, and under
Yeah.
different lighting condition, it does struggle. So
Yeah.
one thing we would have to do, there were certain ideas of how to go around it, perhaps train it under different lighting condition, and have that, or design slightly different architecture for the model to be more generalizable, right?
So for example, one time we had a lot of glare on the track. It was a lot more glossy, and we let the sunlight in, and it couldn't detect the red line, so it couldn't follow it. Yeah, simple. It was crashing. It was behaving erratically. Yeah, 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 yeah.
Driving around in good weather in the desert.
Yeah.
But I always wonder, what about winter conditions or snow?
Yeah.
There's lots of challenges.
Yeah, and also there's a lot of other factors, like what if the surface was wet? We don't have the telemetry data from we don't have sensors on the wheels to collect what is a wheel slipping on the track or not. So that is something that we can also improve on, and we can consider in the next iteration. Version 2, exactly. Yeah. So we factored all those in, but first let's create. Yeah, exactly. Small set. Yeah, yeah.
So how you assemble this one? How you know how to assemble this one?
Yeah. So I personally didn't assemble the car mechanically. I was more involved on setting up the infrastructure to collect the data, train it, and deploy it back. But so assembly, we had a few interns, which if they were here, would be much better able to answer those questions.
Yeah, because I don't know how you design this one.
Yeah. Yeah. So as far as I know, when we started the base of the car, like the wheels and everything that came intact. Then we had to solder all these components, add them onto the car and the sensors to make sure it worked. Yeah. Yeah.
So
Yeah.
look like it's where you have this one to control.
Yeah. Yeah.
So there's some mechanics who design the.
Well, I mean, there was a lot of reinforcement, right? As I mentioned before, and then building out the platform on top of it so we could handle it.
Yeah.
You had a question?
Yeah.
Yeah.
Regarding the sensing system, you use just the stereo camera and the LiDAR only?
For the sensors, yes. Right now, yes.
What about the heading actually? You are not utilizing the heading of the car?
The heading?
The heading, yeah. So you don't need IMU.
The heading, as in the steering angle?
Yeah.
Yeah, so we're collecting that from the car. So that's collected from the car. But in terms of external sensors for your peripheral vision, it's just the camera and something sensing, like, you know, if something's close by as a proximity sensor is something that the LiDAR would act as. Yeah.
So how the car actually would know the track? Does it need actually the heading from the IMU to keep?
Yeah, so that's what we're collecting, right? So for every image, there's a steering angle associated. So when it sees an image, it predicts this is the angle for the steering that I have to take for that. Yeah, yeah.
Oh, I have a question.
Yeah.
Is a real, autonomous driving car using your system, like the new, Hortonworks, Rio?
Yeah.
Is that same? Just like,
Yeah, so the idea was that this is the infrastructure that you can train and run, right? And everything else was written in TensorFlow for the actual modular architecture of the neural net itself.
Yeah.
Basically, my question is that for a real autonomous driving car,
Okay.
like a cruiser, right, for GM, right? They using your system or similar?
Oh, do we have customers using? Do we have? Okay, so the question is, do we have customers using HDP to, create, self-driving autonomous vehicles? That is something that we should look. Yeah.
So the idea is that this is exactly what you would go through if you were training the much larger vehicles, right? You have this entire platform that scales to aggregate, bringing petabytes of data. I mean, you've seen it's 4 terabytes per car. That it's about 4 backup drives each day for a vehicle. That was an estimate that Intel did one time. So now that you have all the data, now you have this training data. Now you can use it to either make simulations, or once you have some of the models deployed, deploy it in real-world conditions and test and see how they behave. So the idea is that these big data platforms, I mean really big because now you're talking about petabytes of data for many cars. Now you can analyze it in real time, and the other part was that you have GPUs that you can pull together to more quickly process and train a model. So like you've seen, there was 5 GPUs in that architecture, 5 servers with 5 GPUs. You can pull them together as one resource and then quickly train the models, test the models, evaluate the accuracy of the models, and then, if the accuracy is sufficient, like in our case, even though it was a drunken driving car, we're like, okay, it's good enough, let's deploy it, let's see how it behaves in the real world.
So you Ubuntu, so how why don't you deploy Red Hat or different operating system? You Ubuntu, can you deploy with Red Hat or other operating system?
It doesn't really matter for which.
It does matter, right? You just
Depending on which drivers, right?
So what is the minor? So this is how many views? Small, single view?
The specs of it.
The specs.
So the question is about the specs of the LiDAR itself. I don't know the specs of the LiDAR itself. It probably doesn't have. It's not as. It doesn't have the resolution as the bigger ones, or probably the speed, because it also has to be power efficient, right? So you take all this consideration. The refresh rate is probably smaller. How much? What?
How much did it cost?
This was
Close to $3,000.
close to $3,000. Yeah.
It's a Velodyne. Is it a Velodyne later?
Is it a Velodyne LiDAR?
I'm not sure. I have to double check. Yeah.
It's probably not exactly very cheap.
It's not cheap. Yeah.
Those are generally the most expensive components that you have in this car.
Yeah.
But again, if you're just training, you could just get away with having a camera, assuming that you would have some kind of emergency stop button. So if the car doesn't behave that your model's predicted in the simulation, then you could kill it and you don't damage your vehicle. Right?
Yeah.
That's the whole idea.
Yeah, that's why we had the LiDAR. We wanted to keep it autonomous and hands-off. So if it's going off track or running into something that it should not be running into, then it can just stop and reverse and get back on track.
And also, this platform itself, these vehicles, if they didn't have all this heavy equipment up, they can go about 60 miles an hour. So they can go really quick. Wow. So one thing that we had to do is make sure that we limit the speed to up to 5 miles per hour. So again, if something goes wrong, if it does hit the wall or if it gets off the track, it won't damage itself, too much. Right? So that was one of those things. So make it a reasonable speed, for these tests. Of course, you could up the ante once you have better models, once you have more accurate models, once you have more training, et cetera, et cetera.
So when it was, I'm sorry.
How many models like this do you have? Only one or two?
The car? How many cars we have? Just one. This is the actual car.
This is the
Yeah.
most prized possession right
Yeah,
now.
yeah, yeah, yeah. The TX2, yeah, Jetson TX2. Yeah.
So when the car was just going back, when there was an obstacle, that was not a part of the training data, right?
No.
So what was it trying to do? Was it trying to like
No, it
dodge?
wasn't. It wasn't trying to avoid it. It was just trying to not run into an object. Simple. We just created a redundancy. If there's something too close to it and its proximity, then it should just reverse to protect the car. Yeah, yeah, yeah.
So
Yeah.
and building on top, you might have seen in the video itself that people stepped in front of it, it would stop. So that was the whole reason to quickly detect, because we wouldn't train it with people walking in the track. So you want to have a safety. The track was just a black surface with red lines. Drive it. That's what the learning component was. This one was a safety because it hasn't seen all these different. You could say actually in this case real world
when there was that
events.
paper or something, it just didn't touch it at all. It just moved back. So I was just wondering.
Yeah.
And that was the whole idea. So the paper would block the laser, block the actual signal.
Yeah.
So it's like, okay, there's something in front of me, stop immediately. In most cases, it will be like if I'm going too close to the wall, stop, back a little bit, make sure I got the image in front of my camera of the road itself, determine what the angle is, and based on what
And
the
then
model
proceed.
predicts,
Yeah.
adjust and move forward.
So just actually for this model only, not the autonomous, very autonomous cars, isn't the camera enough actually for running this?
Yes,
the arena?
it is. It is. It is.
So how would the LiDAR?
Yeah. So the question is the camera enough to have an autonomous car running around a track like that we showcased? And yes, it is. It should be enough. It just depends on how accurate your model is, and you also have to take into account the mechanical constraints of your car. Can it turn sharply enough on the path that you have? So if it's going to run, if the car cannot turn sharply enough to avoid an obstacle, then it was going to run into an obstacle even though it detects it, right? That's a mechanical constraint of that car. So that is something that we did not think of when we got the car and started with the track. We didn't. These are things that came up later, and that's why we had to implement redundancies. That okay, the car cannot turn sharply. It's going to run into an obstacle. Then we have to make sure it backs up. So that's something in hindsight. We say that hindsight's 20/20, right? So if we had known that before, we would have made sure that we had a smaller car, more agile car, or a larger track. Yeah, but that wasn't possible. Yeah.
So why didn't you, if it's just a redundancy thing, why didn't you use like ultrasonic or infrared sensors? Much cheaper than the LiDAR.
Yeah, we just guess. Yeah. Wanted to.
So the question is why didn't we use other sensors? And that is a good point. We're probably going to add those sensors as well to the car itself because it would limit cost. I think initially we just spec the LiDAR because we wanted to do other things with it, sort of like the Google cars want to do actually the laser mapping. So in the future probably we're going to add those sensors. But in this case, like if you did want to save $3,000, you could just have the camera and ultrasound.
Actually, we did do some 2D mapping of our office floors with the LiDAR.
With the LiDAR?
Yeah.
That's good.
Yeah.
So this is cool because with the LiDAR then you can do additional things like simultaneous localization and mapping, right? You can actually map the entire environment.
Yeah.
Exactly. So this is a platform again that we're going to use for a lot of the future development. And so having these sensors right now is very useful as these guys play around.
So what we
It's really good at detecting the line actually.
Yeah.
But I don't know if it sees the floor or not.
It doesn't. No.
So you're saying like
Are you talking about the camera or
the LiDAR?
The LiDAR is really good at detecting lines.
So if you angle it at a certain so basically.
I think you can use it to follow the line, and then
The thing is, you said that the accuracy is based on the model and then compared to someone driving it.
Yeah.
But is it actually learning from driving it in real time, or like if it is one circle?
Yeah.
Then you put it back to the model and it uses that data.
Yeah.
And what kind of score do you use? Like what kind of variable do you use to say that it is a better circle track than the one before? You know what I'm talking about?
Yeah. So that was more of a trial and error at that point of time. So what we did was we ran the car around the track multiple times, collected data, and more and more. So for each second, we're collecting 30 frames, and for each frame, there was a steering angle associated with the data. And then after each iteration, the more it learned, the more accurately we actually drove it around. We saw some the car. So that's the bare bones of where we started. That's how we checked the accuracy of the model and made sure that when it's actually predicting the value from the model, is it similar to the human steering angle that we gave when we were going around the track. So when we're going around the track, we're trying to turn at some point. So it collected the steering angle of the car at that point based on that image. So when it was actually predicting the value of which steering angle it should take at that point of time, we're just trying to compare. Oh, it's similar. It's more closer to the one we had. That's how we did calculated accuracy. Yeah.
So actually, I have a question for you. If we were to now improve the accuracy, go the segments of making sure that it drives better in this environment, it's got less of this drunken type of driver behavior, what will be the next steps?
Okay, so I think the next step is definitely that we want to gather more data because right now we're just using we get the training data for several minutes or half an hour. So with the more data we gather, the better the model we can generate, because the basic idea is that I mentioned in the simulator session. So we gather the image as well as the steering angle, and we pop in the image into the convolutional network to train the model. So we'll keep doing these things until we find the loss. Compare with our human drive the steering angle command. So we'll compare this the difference, and as the time goes on, as the data we gather more data. So our objective is that we try to decrease the difference, decrease the loss. So when we maintain the loss in the reasonable percentage, we'll can validate that the model is ready to use. Okay, so I think that's the one thing we can improve. And another thing is that we can try a different environment. Like right now we just use one single track. So that will make the model just more specific for that kind of environment. So we will explore the different tracks or different environment, like in the sunny environment or in the rainy environment. That will give the model more scenario to try on to gather the data. Because so think about the gather more data with one track as the go deeper, and try different tracks, different environment, like go wider. So we want to improve both of these dimensions to make the model better. Yeah.
So when you collect that data, do you also collect the data when there are multiple cars? So how do you handle the scenario when there are multiple cars with different speeds? And
So we haven't gotten to that point yet.
Yeah, so I think that's a very good question. So right now we just use one single car to because we try to generally build a working model. But if we have different cars running together, and we want to make sure that these cars didn't make collision with each other, I think that's a totally different environment.
And in that case, is the camera 180-degree view, or?
It's more like
so this is 120 maybe.
120.
So this is like the normal.
Yeah.
So this one is like the normal Logitech camera. So it's not. Yeah. So we have another one which has wider, which can generate the 3D cloud, but we haven't used that because that one is too high, and so it cannot see the red lines in the middle. So we use this one. Yeah, because this one can tilt. So we have another one which is fixed. You cannot tilt. So that one. Yeah.
So we tried multiple cameras. Yeah. Just to figure out the right one for this car. So it's a trial and error process.
For the typical autonomous driving car, right, you need to test like that. You can see the traffic light, then red light, they can stop, turn left, turn right. Like you didn't do that.
Yeah. So there are many other technologies can be used here. So for example, if you drive in the real environment, you have to do the image segmentation, which it knows. Oh, this part is human. Don't go that part. That part is a traffic light, like that. Yeah, and also some algorithm needs some space planning. It will look at the cars around itself and see how many space we can use. And when we driving, say, hey, there's a corner, we can speed a bit, but we need to turn right earlier, like that. So there are many other technologies needs to be combined with deep learning. Deep learning just solve one part of the problem. Yeah.
Other questions, guys? Actually, I'm not a machine learning guy, but I'm the control side. So I'm just wondering actually if you are doing any sensor fusion between the two sensors, the LiDAR and the camera, or you don't need that in the deep learning. You are reading everyone actually separately.
So basically the LiDAR can be used if you have light, for example. But when we have light, we will only use an image. But you can so you can imagine we can combine the two models. We can combine the two models when we can make some better decision. So which is the real car companies doing? Real car companies will train many different models using different sensors, and they will give different feedback. And for example, the camera may say you are too close, but the LiDAR says you are okay, but the car will still stop. So there are some kind of things like that. Yeah.
Questions? Okay, with that, we're going to finish up with the online portion. Thanks, Liang, and we're just going to hang around. Thank you very much.